In this video, we want to think about integrals where the antiderivative function results in some kind of inverse trig function. Now, you'll remember from trigonometry that the inverse trig functions are not one-to-one unless their domains are severely restricted. For arcsine, that meant between negative pi over 2 and pi over 2. For arctangent, it went from negative pi over 2 to pi over 2 as well, but didn't include the endpoints negative pi over 2 and pi over 2. When we think about arc secant, we'll go from 0 over to pi, but we'll leave out pi over 2 since cosine is 0 there. Now, we won't have to be as concerned about that as we were in trigonometry, but we are going to be looking at antiderivatives that involve the inverse trig functions. Now, remember, when we did take the derivatives, we were finding that the derivative of the inverse trig function generally resulted in some kind of radical expression or a rational expression. Now we want to do the reverse. That is, we're going to start with the radical expression, generally in the denominator, or the rational expression, ratio of two polynomials, and we're going to find the antiderivative function. The antiderivative function will involve an inverse trig function. We'll also need to do some U substitution as part of this process. In fact, the formulas that we're going to use are not ones that we're going to prove in this class. We'll actually prove them when we get into Calculus 2. What we're going to be doing in Calculus 1 is instead taking the formula and applying a form of U substitution to convert the original integral into the integral in the formula, so that we can use the right-hand side of the formula for the antiderivative function. Just to remind us where we're starting from, let's take a look at the derivatives of the inverse trig functions again. When we're looking at the derivatives of the inverse trig functions, you'll remember that the derivative of the inverse trig function, or arcsine, gives you 1 over the radical of the expression 1 minus u squared times the derivative of u with respect to x, and it carries a restriction on it due to the restriction on the domain of arcsine. Then we have the derivative of the arctangent function, which gives us the ratio of two polynomials, 1 over 1 plus u squared, also times du dx. This time there's no restriction on u. The last one we're going to talk about in this section is the derivative of arc secant. We find that this gives us 1 over the absolute value of u times the radical of u squared minus 1 times du dx, with the restriction that the magnitude of u be greater than 1, so that what's under the radical turns out to be strictly positive. Now, when we're looking at these, notice that 2 of these involve a radical, and the same 2 have a difference. Notice that the one that involves arctangent does not have a radical and it has a sum. Now let's do the reverse of this operation and start with what's on the right side and take the antiderivative function to come up with the inverse trig function. We're going to compare these one at a time, looking at each one. First, we want to look at the integral of du over the radical a squared minus u squared. The integral of this is very similar to what you see on the right-hand side of the derivative formula. The difference is the derivative formula has a 1 minus u squared, and the integral formula has a squared minus u squared. Now, a squared cannot be the variable because the differential is du, which indicates that u is the variable. That makes a squared a constant term. And this will give us the arcsine of u divided by the absolute value of a up to the constant of integration, that family of functions. Now let's take a look at the one that will come up with arctangent. And I'll scroll it down just a hair more. When we're looking at this one, the derivative formula gave us 1 over 1 plus u squared. But notice in the integral formula, we have 1 over a squared plus u squared. Again, a squared and a cannot be variables because the differential is du. That makes a squared a constant term. The result gives us 1 over a, the arctangent of u divided by a, up to the constant of integration. Let's look at the last one we're going to consider in this section, which is the one involving arc secant. The derivative formula gives us the absolute value of u in the denominator multiplied by the radical of u squared minus 1. When we're looking at the integral formula, notice that the u that's in the denominator is not in absolute values. This is a difference between the two. Also notice that it does not have a minus 1, it has a minus a squared. This results in 1 divided by the magnitude of a, or the absolute value of a, times the arcsecant of the magnitude of u divided by a, up to the constant of integration. Now again, we are not going to prove these formulas. Normally, we go through the process of actually integrating. We're not actually integrating. What we're doing is we're going to take an original integral, something over here, and convert it by substituting for each piece until it looks like one of the three on the left. Then we're going to use the formula that's on the right side to express the antiderivative function in terms of the inverse trig formulas. Now let's talk about choosing the correct formula from the three formulas we have. What we want to do is we want to look first at the denominators. If the denominator has a radical with a difference underneath it, then it has to be either arcsine or the arc secant formula. In that case, you want to take a look at whether or not it's the constant term minus a variable term, or whether it's the variable term minus the constant term. When it's the constant term minus the variable term, then it must be arcsine. Then we'll do a u substitution on the variable term, which will let us determine what u is. We'll have a squared so we can find what a is. Knowing what u is, we can take the derivative of both sides and abuse the notation to solve for dx in terms of du. Now, if we have instead the variable term minus the constant term, then it must be the arc secant formula. We'll do the same thing. We'll do a u substitution on the variable term, finding a, finding u, find the derivative of u with respect to x, and then using that to solve for the differential dx. On the other hand, if we look at the denominator and we see a sum of two terms, no radical and no difference, one a constant term and one involving the variable, and we know it must be the arctangent formula. Again, we'll do a u substitution on the variable term. In general, we're going to have to find what to use to substitute for a squared, u squared, and then taking their principal square roots to get a and u. In other words, we typically use the principal square roots, or the positive ones, when finding a and u. We will also need to know how to apply the formula and how to solve for dx. So we're going to have to find du first by taking the derivative with respect to x of the expression for u. And then we'll be able to find du dx. We'll abuse the notation and swing the differential to the other side, and then we can solve for dx in terms of du. This will let us substitute part of the original integral dx into something that has du in it. We'll need to be able to do that in order to convert the original integral into the integral on the left side of the formula. Before we can get the right side of the formula, we have to have the left side of the formula, which has du, a squared, and u squared, and does not have a dx in it. Integrating a formula from the integral tables, which is what we're doing, generally involves a lot of pattern matching and a lot of substitution of one expression for another, and generally a u substitution and a substitution for the differential dx. Don't forget, if it's a definite integral, that we'll need to change the limits of integration to u values. instead of x values, since the differential in the formulas is du. Now let's take a look at example 1 and see how we can apply the pattern matching process. Our original integral is the integral of dx over the radical of 1 minus 16x squared. When we look at the three formulas that we have on the left side, we notice that we have a radical and a difference, which tells us it either is arcsine or arcsecant, one of the S inverse trig functions. Because it is a constant 1 minus a variable term, 16x squared, that is most like the formula for arcsine, the one that is 1 over the square root of a squared minus u squared. Remember, the differential, which is du, indicates that the variable is u, which makes a squared the constant term. This becomes the arcsine of u over magnitude of a up to the constant of integration. Let's now write down the pieces that we've discussed. We know that the a squared becomes the constant term, which is the 1. That means that the principal square root is 1. Again, we typically use the principal square root when applying these formulas. When we think about u squared, which has to have the variable in it, we see that this becomes the 16x squared. Notice that both formulas have the subtraction in it. So u squared does not include the subtraction. It is simply the 16x squared, the variable term following the subtraction. Then we apply the principal root again, and that we get u is 4x. Now we take this expression for u and we apply the derivative with respect to x to both sides. That gives us the derivative with respect to x of u equal to the derivative with respect to x of 4x. That gives us du dx, which is equal to 4. Then we abuse the notation as we learned to do previously, and we swing the dx around to the other side. Now, technically, we're not allowed to do that because this isn't a fraction, it's the derivative operation. But the genius of Leibniz's notation is that if we do that, it works, and it always works. So we do it. This gives us du is equal to 4 dx. Now we solve for dx by dividing both sides by 4. Now we have something to represent each piece in the original integral to convert it into one that looks like the integral on the left side of the arcsine antiderivative. Now what we want to do is substitute. So we have the integral of dx over the square root of 1 minus 16x squared equal to the integral. We replace the dx with du over 4 over the square root, replacing 1 with a squared and replacing 16x squared with u squared. Notice that we have a du over 4 on top. The 1/4 is a constant factor, which can be factored out of the fraction and indeed out of the entire integral and brought to the front. This becomes 1/4 the integral of du over the square root of a squared minus u squared. With the exception of the constant factor 1/4, it's now identical to the formula we see on the left, which means we can now use the formula part on the right as the antiderivative function. This gives us arcsine of u over the magnitude of a up to the constant of integration. We still have the 1/4 as a factor on this, so that we end up with 1/4 the arcsine of u over magnitude of a plus the constant of integration. Now we know that u is 4x, and we know that a is 1, so we can substitute those into the expression so that we can write the antiderivative function back in terms of x, since the original function was itself in terms of x due to the differential dx. This then would give us the final solution, 1/4 arcsine of 4x divided by 1, which is 4x, plus the constant of integration c. Now I know that some of you are very tempted to want the 1/4 and the 4 to cancel. But the 1/4 is a constant outside of the inverse trig function. And the 4 is a part of the argument for x, which is inside the inverse trig function. Never, ever, ever pull a constant out of the argument or move a constant into the argument. What's in the argument to an inverse trig function stays in the argument. What's not inside the argument stays outside the argument. Now let's take a look at example 2. In example 2, we again have an integral of dx divided by the radical of 9 minus x squared. The radical and the subtraction is a dead giveaway that this is probably arcsine or arcsecant. Because it is a constant minus a variable, it is again going to involve the arcsine as part of the antiderivative function. We now need to take this original integral and convert each piece until it looks exactly like the formula on the left, up to maybe a constant, so that we can then use the antiderivative function on the right. Looking at the pieces, we can see that a squared must be 9. Therefore, the principal root of a squared is going to be a equal 3. Then we have that u squared, not including the subtraction, must be x squared. The principal root then tells us that u must be x. Now we take the expression for u, which is equal to x, and take the derivative with respect to x of both sides so that we can get an expression for dx in terms of du. Again, this leads to the derivative of u with respect to x and the derivative of x with respect to x, which gives us du dx equal to 1. Abusing the notation and swinging it around, we get that du is equal to dx. This should not be unexpected since u was x in the first place. The differential du is the differential dx. Now we have something to replace each piece. And so what we're going to do now is we're going to substitute a squared for 9, u squared for x squared, and we're going to substitute du in place of dx in the original integral, so that we have the integral of dx over the radical of 9 minus x squared becoming the integral of du over the radical of a squared minus u squared. Check to be sure that other than a constant multiple at the front, this is identical to one of the 3 formulas that we have for this section. It's the first one, which gives us arcsine of u over the magnitude of a up to the constant of integration. This gives us arcsine of u over magnitude a to the constant of integration. Now, remember that our constant of integration is giving us a family of antiderivative functions. In other words, the same graph shifted up and down by some constant c. Now, what we're going to do is we're going to go back to the original, since it was originally in terms of x, and get the antiderivative function in terms of x. So we replace u with x, and we replace the absolute value of a with 3. This leads to the arcsine of the argument x divided by 3 with the constant of integration c. This is the antiderivative function for the original function that you see here. If you were to take the derivative of this function, you would come back with the integrand function that you see here. Remember that the derivative of the constant would be 0, so the c would drop off. Let's now take a look at example 3. In example 3, we see something that we haven't seen before. In this particular integral, we do not have a radical, and instead of a difference, we have a sum. That's a dead giveaway that it's not arcsine and not arcsecant. It's got to be arctangent. The way that I remember that is I think of the t in the tangent as a plus sign. And the fact that the denominator has a plus sign and no radical is an indication that it's the arctangent function, which you see here in the center. Let me put a box around it to make it stand out a little bit more. Now what we want to do is we want to take our original integrand and we want to replace each part of the integrand and the differential dx with something so that it can be rewritten in the form of du over a squared plus u squared. By matching the pattern of the two together, I can see that 25 must be a squared. That means that the principal root is going to be 5, so a is 5. I can see that u squared, the expression with the variable, must be the 4x squared. The principal root then would give me 2x. This expression for u is the one that we take the derivative of both sides in order to get an expression for dx. We cannot say that du is equal to dx. They're not. This is the differential with u as the variable. This is the differential with x as the variable. They're not the same, but they are related. They're related through this equation here. So we take the derivative of both sides of that equation with respect to x, and we get that du dx is equal to 2. Swing the dx to the other side, called an abuse of notation, then solve for the dx by dividing both sides by 2. Now I have something to substitute into the original integral for my dx, which is du over 2. My 25 will be replaced by a squared, and my 4x squared will be replaced by u squared. Starting with the original integral in terms of x, dx over quantity 25 plus 4x squared is equal to the integral of du divided by 2, all divided by a squared plus u squared. Now the 1 over 2 is a complex fraction, but remember that I could pull this out as 1/2 multiplied by the fraction. So the 1/2 is a constant multiple, which I can actually pull out of the fraction and out of the integral. And I can rewrite it as 1/2 times du over a squared plus u squared. Now the formula that I have here is exactly the same as the formula I have on the left side of the one with arctangent up to the constant multiple of 1/2. So now I apply the formula on the right side to what I have here in the integral. This becomes 1 over a arctangent of u over a plus a constant. I still have the 1/2 at the front, and it gets multiplied by everything that comes after. 1 over a becomes 1 over 5. Then I have the integral of a squared plus u squared in the denominator becoming 1 over a arctangent of u over a. So I add the arctangent of u over a plus a constant. Now, the next thing I need to do is substitute for u and a in the argument for this formula. A is 5 and u is 2x. And again, we use the principal roots. This gives me 1/2 times 1/5, the arctangent of 2x over 5 plus c. Now, remember that we can distribute the 1/2, and I get 1/2 times 1/5, which gives me 1/10. The arctangent of 2x over 5. Again, do not be tempted to pull the 2/5 out of the argument. It is a part of the argument of the inverse trig function and must stay there. You cannot also put the constant outside the inverse trig function into the argument. Now let's talk a minute about what happens when I distribute the 1/2 over the c. I get 1/2 c. But c is an unknown constant of any value, and half of a constant is still a constant. So we roll the 1/2 into the constant, and we still call it plus c. Is it the original c? No, it's half of the original c, but it's still a constant. So we roll in the 1/2 and just call it plus c. This is as simple as this antiderivative function gets. Now let's move on to example 4. In example 4, we see the original integral as dx divided by 16 plus x squared. Again, the denominator does not have a radical, but it does have a plus sign. T for plus, arctangent. Again, the center one in our list of functions. And in case you're wondering, I do not expect my students to memorize this formula. We'll actually learn a method in Calculus 2 to derive the formula, a method or a process to find it, which generally is easier to remember than a formula. So all we need to do is convert each piece, the 16, the x squared, and the differential dx, into du, a squared, and u squared, so that we can use the right side of the formula as the antiderivative function. We can tell by matching the pattern that a squared, the constant, must be 16. This means that we have a equal 4. Again, we use the principal or positive root. We can also tell that u squared must be x squared, which implies that u is equal to x. Now we take the derivative of both sides of the relating equation where u is equal to some expression of x, so that we can solve for dx in terms of du. That will let us substitute for the differential dx and convert it into something involving du. When I take the derivative of both sides, as we've seen in a previous problem, this simply means that du dx is equal to 1, which implies that du is equal to dx. Now I have something to substitute for each of the 3 parts of the original integral. Now I can rewrite the original integral of dx divided by 16 plus x squared as the integral of du divided by a squared plus u squared. This integral, which didn't need a constant multiple, is identical to the left side of the formula coming from the integration tables. Now I can use what's on the right side in either the inverse tangent function notation or the arctangent notation to represent the antiderivative function. I prefer arctangent instead of inverse tangent notation because I don't like the fact that the -1 looks like a power, although it represents the inverse function. So I stick with arctangent. This is going to give me 1 over a, the arctangent of u over a as the argument, plus the integration constant. Now I can use the pieces of the formula that I used for substitution, and I can replace a with 4, giving me 1/4 the arctangent of u, which is x, over 4, plus the constant of integration. Again, do not move any part of the argument to the arctangent out of the argument. That's never allowed. I don't get to say never very often. It is never allowed. You also cannot move the 1/4 inside the argument. That is never allowed. This is the best way to leave it. Now, thus far, we have focused on finding antiderivative functions because we've had indefinite integrals. If you have a definite integral with limits of integration on the integral symbol, then you also have something else that has to be converted, namely the limits of integration. Let's take a look at example 5, which is a definite integral. When we're looking at example 5, we'll have to replace the differential dx with an expression involving du. We'll have to replace the 4 with an a squared and the x squared with a u squared. But we also have to replace the 0 and 2. And the reason is, even though it's not typically written, these represent x equals 0 and x equal 2. They match the variable in the differential. And in the formula, we're going to have a differential, no matter which formula, of du, which means that these limits of integration need to be u values. So now we're going to proceed, much as we did for the indefinite integral. We're going to find the antiderivative function. After we do, we will plug in the limits of integration as u values and subtract them to find the area between the curve and the x-axis. This is not finding an antiderivative function at all. This is finding the area between the curve and the x-axis. Now let's take a minute and substitute each part. Again, we have a squared equal to 4, which means that my a is equal to 2, just as we've been doing. My u squared is equal to x squared, which means my u is equal to x. Then I can take the derivative with respect to x of both sides of the relating equation u equal x to get du dx equal to the derivative of x with respect to x, which of course is just 1. That then tells me, by swinging the differential dx to the other side, that du is equal to dx. Again, this is an abuse of notation, which shouldn't happen, but it works, so we do it. But again, this does not represent a fraction, but treating it like one works for the notation, again, so we do it. Now we have something for the 4, which is a squared, something for the x squared, which is u squared, and we have something for the differential dx, which is du. We need something to replace the limits of integration x equals 0 and x equal 2. This is going to be a faster way of doing it than back substituting. So we're going to find that when x is equal to 0, u, which is x, is also equal to 0. And when x is equal to 2, u, which again is equal to x, is also 2. So that we find that in this case, because u is equal to x in the relating equation, that the limits of integration actually don't change. Because u and x are equal, their limits of integration are also equal. This does not usually happen. Usually, u is an expression involving x, but not just x, which would mean that the limits of integration would change from their x representation to their u representation. Now let's substitute each piece into the original integral. We're going to have the integral from x equals 0 to x equal 2 of dx over 4 plus x squared equal to the integral from u equals 0 to u equal 2 of du divided by a squared plus u squared. Again, I substituted du in place of dx. I substituted a squared in place of 4 and u squared in place of x squared. I substituted u equals 0 for x equals 0 and u equal 2 for x equal 2. Now I wrote the x equal and the u equal on the limits of integration to emphasize that we're going from x values to u values. The differential is du, so the limits of integration must match. Now the formula looks identical to the formula we have for the one involving arctangent in the antiderivative function. Let me draw a box around it to make it stand out. Because I have an integral that looks identical to the formula on the left, other than the limits of integration, I can use the antiderivative function. And then I can plug in the limits of integration and subtract them. Now I'm allowed to use any of the antiderivative functions that I want. I have 1 over a arctangent of u over a plus any constant on Earth, any real value. But the easiest one to choose is the one where the constant is 0. So I'm going to choose c to be 0, and I'm going to use the antiderivative of 1 over a arctangent of u over a, which is going to be 1 over a arctangent of u over a evaluated between u equals 0 and u equal 2. Now, some students get confused here. In the indefinite integral, when we were looking for an antiderivative function, we then back substituted and got out of u to go back to x, because the original integral had the differential dx, meaning the variable was x. We needed to write the antiderivative function in terms of x. In this case, though, we are not looking for the antiderivative function. The definite integral is the area under the curve. This link that you see here in the window will take us to a graph of this particular function in the original integrand, and it will look at the area that we have between the original limits of integration, x equals 0 and x equal 2. Let's take a look at what that looks like. This is the original function that was in the original integrand, 1 over 4 plus x squared. And we are shading the region between x equals 0 and x equal 2, which you can see right here is shaded in blue. This particular function, because the denominator is always strictly positive, is all above the x-axis. And then we take the vertical lines at x equals 0 and x equal 2, and we're looking for the area between the curve and the x-axis. That's the definite integral. That's a number, which represents that area, the number of square units. Going back to our example then, we are not looking for an antiderivative function. We are instead looking for a number answer, which represents area between the curve and the x-axis. That means that we want to stay with u, since our limits of integration are u values, but we can substitute what a is. If we scroll back up, we find that a in this problem was 2. Substituting this into our expression, we then have 1 over 2, the arctangent of u over 2, evaluated between u equals 0 and u equal 2. Again, you do not normally have to write down what the variable is in the limits of integration. I do it to emphasize that they are u values, and that matches the variable in the expression. Now we're going to substitute them in. The 1/2 is a constant, which we can pull out of the entire thing and keep on the left side. Then we take the arctangent of u over 2 and substitute 2 in for u. That gives us the arctangent of 2 divided by 2. Then we subtract what we get when we substitute the lower limit of integration into the antiderivative function we chose. This would give us arctangent of 0 over 2. Now, we know that the arctangent of 2 over 2 is going to simplify to the arctangent of 1. And the arctangent of 0 over 2 is going to simplify to 0. Now we need to decide what these come out to be. Remember that the arctangent is in fact an inverse trig function, which says the angle between negative pi over 2 and pi over 2, whose tangent is 1. The arctangent represents the angle, theta, where theta has to be in that restricted domain from negative pi over 2 to pi over 2, open, where the tangent of it is 1. Let me write this down. This represents theta in open negative pi over 2 to pi over 2, the domain for the arctangent, which is, or rather the range for the arctangent, which is going to give us the tangent of theta being 1, all right? Now, when do we get the tangent of an angle equaling 1? If it equals 1, then when we write it in terms of sine and cosine, we know that the sine and cosine are equal. Tangent is sine over cosine, and if we get 1, they have to be the same. Well, that means it has to be a 45-degree angle, or pi over 4. Because it is a positive 1, it's got to be in quadrant 1, since the region between negative pi over 2 and 0 is in quadrant 4, and tangent is negative there. So that tells us that the arctangent of 1 would give us basically a pi over 4. What about the second one? When I look at the second one, arctangent of 0 represents theta, again between open negative pi over 2 to open pi over 2, such that the tangent of the angle is 0. Tangent is sine over cosine. When is sine 0 but cosine not 0? Well, when the angle is 0. So this second one is going to give us an angle of 0. This gives us 1/2 times the difference of pi over 4 minus 0, which of course comes out to be pi divided by 8. That is a constant number, which represents the amount of area you see here underneath this curve, between the curve and the x-axis. Now remember that 1 square unit would be going from 0 to 1 on both the x and the y-axis. So we can see that this amount is actually a relatively small amount of area, less than 1 square unit. And that fits with what we got for pi over 8. Now let's look at example 6. Example 6 is back to being an indefinite integral because there are no limits of integration. Looking at the denominator, we do see a radical and we do have subtraction. We also have the variable outside the radical, which is new, something we haven't seen before. But again, we want to focus on the radical and what's underneath the radical to distinguish the formula involving arcsine from the formula involving arcsecant. Arcsine is a constant minus the variable term. But what we have is a variable term, 4x squared, minus a constant term, 16. This must be the formula involving arcsecant, which is the third one that we are learning in this section. Now what we need to do is translate each part in the original into something so that it looks like the formula on the left side. Once we have it identical to the formula on the left, we can use the antiderivative function on the right as the value of the integral. By looking at this and looking at this, I need to equate pieces. However, du is not dx. The variable being u is not the same as the variable being x, which also means that u and x are probably not the same thing. However, under the radical, the u squared does have to be 4x squared, and the a squared does have to be the 16. You always start with the u squared and the a squared. Let's write down what we have so far. A squared is the 16, not including the subtraction. and the principal root of it, the positive one, is 4. U squared, which is the expression involving the variable, is 4x squared. Taking the square root of that and making it the principal root leads us to u equal to 2x. This is our relating equation. When we look at this equation, it relates u to x. This is what we're going to use to replace the differential dx with some expression that will involve du. We're also going to use that same equation to find an expression for x in terms of the variable u. So when we're looking at it, we can do this in 2 pieces. First, we know that we're going to take the derivative with respect to x of both sides. We've done this on every equation we've had so far. This gives us du dx equal to 2. Abusing the notation swings the dx around, and solving for dx gives us du over 2, which is an expression that we will use to substitute for the differential dx. What about the x, though? Again, go back to your relating equation. If u is equal to 2x, then it must be that x is equal to u divided by 2. Now that we have this, we have something that we can substitute in place of the x, which is in the original integral, with something that relates to u, which can be used over here in the denominator where we have the u. Now let's substitute each piece that we have. The integral of dx over x times the radical of 4x squared minus 16 gets translated. The dx becomes du divided by 2. This is going to give us a complex fraction. Now we need to divide this fraction by some expression for x. Scrolling back up again, we can see that what we got for x was u divided by 2. So we replace this x with u divided by 2. Now we want to replace what's under the radical. The 4x squared gets replaced with u squared. And the 16 gets replaced with a squared. Now this almost looks like the formula we have on the left for the one involving arc secant, but not quite. We have these fractions, this 1 over 2 and this over 2 in the denominator. This makes it into a complex fraction with 4 parts: the numerator of the numerator, the denominator of the numerator of the denominator, and the denominator of the denominator. When we convert this complex fraction, the denominator of the denominator is actually supposed to be in the numerator. I can rewrite this in strictly complex form as du over 2 over u times the radical, u squared minus a squared over 2. Make sure that your primary division bar is longer than the other 2, so you can keep track of where the pieces belong. Now, what I said was the denominator of the denominator is actually the numerator, or as I like to tell my class, the bottom of the bottom is the top. So the 2 becomes the numerator of the numerator up with the du. That means that I get the integral of 2 times du over 2 over u times the square root of u squared minus a squared. Now the 2's will cancel. And when the 2's cancel, I'll be left with exactly the formula that involves arc secant. This is going to give me du over u radical of u squared minus a squared. You can see now that this does exactly match the formula I have on the left coming from the integral tables. Again, we're not proving why this equals this. I'm just telling you, you have to take it on faith until you get to calculus 2. When you get to calculus 2, you'll learn a method called trig substitution, which will allow you to prove that this is equal to this. Now what we want to do is we want to take, because it is the formula on the left, we want to use the antiderivative function on the right. So this is going to be equal to 1 over the magnitude of A times the arc secant of the magnitude of U over A plus the constant of integration. Now, this was an indefinite integral. We are not looking for the area under a curve, so we're not looking for a number. We are looking for an antiderivative function. The original integral was in terms of x due to the differential dx. We need to return the antiderivative function to a function of x. So we will substitute for u 2x and for a 4. This gives me 1 over 4, the arc secant or inverse secant function of 2x over 4. And again, you could leave this in absolute values plus the constant of integration. Now, I can reduce the 2x over 4 because they're both inside the argument to the inverse trig function. And I could write this as x over 2 plus the constant of integration. I cannot pull the 1/2 out of the argument, nor can I put the 1/4 into the argument. Keep those parts apart. Now let's move on and take a look at the next example, which is example 7. Example 7 is a definite integral. We can see that because it has limits of integration. Now we want to evaluate this to decide which of the 3 formulas on the left fit it best. It has a radical and subtraction. So it's either arcsine or arcsecant. When we look at it next, we want to see if it's constant minus variable term or variable term minus constant. Since it's constant minus variable term, it's got to be the first one, which involves arcsine as the antiderivative function. So we want to match the pattern of this first formula from the integration tables. Looking at the pieces, I know that a squared is equal to 1. So a, the principal root, is 1. I know that u squared is equal to x squared, so that u is equal to x as the principal root. Now I can use this relating equation that I have right here in order to find an expression involving dx to substitute for the differential. This gives me the derivative with respect to x of u equal to the derivative with respect to x of x, which gives me du dx equal to 1. This tells me that du is equal to dx, which we have seen before. Now I have something to substitute for the differential dx. I have something to substitute for the 1 and something to substitute for the x squared. This will give me essentially what you see in the indefinite integral here in the formula. It does not, however, replace the limits of integration. These are x values. This is x equal to -1/2 and x equal to 1/2. So then I replace those by saying when x equal -1/2, u, which by the relating equation is x, stays the same and becomes -1/2. When x is equal to 1/2, u, which is still x, is also a half. We will see an example shortly where the limits of integration change because u is not equal to just x. Now we have something to substitute for each piece. So let's replace our integral from x equal -1/2 to x equal 1/2 of dx divided by the radical of 1 minus x squared with the integral from u equal negative 1/2 to u equal 1/2. To replace the differential dx, I have the expression du. And to replace the 1, I have a squared. And to replace the x squared, I have u squared. Now it looks exactly like the formula on the left involving arcsine. That gives me the antiderivative function of arcsine of u over magnitude of a up to a constant of integration. This is a definite integral, so I'm looking for area between the curve and the x-axis, which is a constant number. This means that I can choose any antiderivative function I want, and the simplest is to choose the constant c to be 0. So I have arcsine of u over magnitude of a. And this is going to be evaluated between u equal negative 1/2 and u equal 1/2. Because I am evaluating this as a definite integral, I do not return to the original variable x. Instead, I keep the limits of integration as u values, and I keep the variable as u. But I can replace the magnitude of a with what a was equal to, which was 1. Then I can write that this is equal to the arcsine of u evaluated between u equal negative 1/2 and u equal 1/2. Now, when I'm thinking about this one, again, I want to substitute this value into the antiderivative function. So I'm going to substitute the upper limit and then subtract when I substitute the lower limit. So this is going to give me the arcsine of 1/2 minus the arcsine of negative 1/2. Again, this represents the angle theta in the closed interval, negative pi over 2 to pi over 2, the domain for arcsine, such that S period T period, the sine of theta is equal to 1/2. And this one represents theta, again in its domain, negative pi over 2 to pi over 2, such that the sine of theta is equal to negative 1/2. That means that I'm looking in quadrant 4 going backwards or quadrant 1 moving forwards. So when I'm thinking about where I am, I need something where the y value is a 1/2 on the first one and positive, and on the second one, where the y value is a negative 1/2 on the unit circle on the second one. The angle that gives us a sine of 1/2 is pi over 6. Remember to use radian measure when you do your inverse trig. This is going to give me pi over 6 to replace arcsine of 1/2. Then I need to look at the second one. This minus is this minus, which is coming from subtracting the values plugged in from the limits of integration. Now, the angle whose sine is a negative 1/2, that is between negative pi over 2 and pi over 2, is in quadrant 4 moving backwards. That means that this angle right here on this particular triangle is negative pi over 6. That gives me a double negative, which gives me an addition. And that gives me 2 pi over 6, which reduces to pi divided by 3. That's close to 1 square unit of area under the curve. Now let's see if I added in a link to look at the graph. You can see right here that I did add in a link to look at the graph. So let's go ahead and click on this and take a look at the area under the original curve. Let's scroll back up to find the original integrand, which is the expression 1 over 1 minus x squared under the radical. Then we want to graph this between x equal negative 1/2 and x equal 1/2. You can see here that I've got the graph of 1 over the radical of 1 minus x squared, which is showing up here in green. And then I've shaded the region between x equal negative 1/2 and x equal positive 1/2, which is this blue shaded region right here. If you look at the blue shaded region and estimate its value, you can tell that it is close to, but probably a little bit less than 1 square unit, which perfectly corresponds to the value that we found for the area under the curve, which we found to be pi divided by 3. Now let's look at example 8. In example 8, we have something that we have not seen before. It is an indefinite integral, so we're not looking for area under a curve, we're looking for an antiderivative function. But this time, not only do we have the radical with a difference in the denominator, but we actually have arcsine, or the inverse sine function itself, as part of the integrand. You got it. This is U substitution of a different type. We're going to have to substitute for each of these pieces. We're going to have a U to replace the arcsine of x, and then treat it as U substitution, where the derivative of U is 1 over 1 minus x squared. Remember, way long time ago, we talked about the derivative rules. And the derivative of arcsine of U is 1 over radical 1 minus u squared times du dx. If the argument to the function is just x, derivative of x with respect to x gives us a 1. Now looking back at example 8, this means that we can take u to be arcsine of x. This is not the same u from the formula. This is a different u. So let's put it in quotations. Different u. U is arcsine of x. Well, I'm treating this as a u substitution problem. So I'm going to do the derivative of u with respect to x, which would be 1 over the radical of 1 minus x squared times the derivative with respect to x of x, the argument to the arcsine. Derivative of x with respect to x is 1. So this gives me 1 over the radical of 1 minus x squared. Then I can abuse the notation and swing the differential dx to the other side to get du is equal to dx over the radical of 1 minus x squared. This is a u substitution within a formula to solve for an inverse trig in the antiderivative function. Now let's take a look and see what we get coming out of here. We're going to substitute for the pieces that we have. We have, for example, that dx over the radical is equal to du, which means that I can take the original expression and I can write it as arcsine of x times dx over the radical 1 minus x squared, which can be rewritten since my u, not from the antiderivative formulas here, but from u substitution out of section 5.5. And I can say that this is going to be u replacing arcsine of x with du replacing the dx over the radical of 1 minus x squared. This gives me u du. Now that is a very simple power rule integral. The differential du tells me that u is the variable. This is u to the first power. So I can apply the power rule on the next step. And when I apply the power rule, This is going to give me u to the 1 plus 1 divided by the new power plus a constant. That gives me u squared divided by 2 plus c. Now, the original integral was an indefinite integral, which had the differential dx. And the original integrand was in terms of x. Because we're not getting area under the curve, which is a constant, we need to return our antiderivative function to being a function of x. So I come up here where I have u equal to arcsine of x, and I replace this u, which is not the u from the formulas that you see here on the left, and I replace that u instead with the arcsine of x. This becomes 1/2 arcsine of x quantity squared plus a constant. Now again, in some textbooks and with some professors, they will take the 2 and put it between arcsine and x, which represents the same thing, that you have arcsine of x times itself, and then multiplied by a 1/2 up to the constant of integration. Let's take a look at one more final example. Let's take a look now at example 9. In example 9, you can see that we do have a radical with a difference in the denominator, which tends to suggest an antiderivative involving arcsine or arcsecant. But we also have a trig function tangent in the numerator, and composed inside of tangent, we have arcsine of x. Now we know from the problem we just did that the derivative of arcsine of x is 1 over the radical of 1 minus x squared. So we can then let u be the argument to the tangent function. That means that we're going to choose u, which is not this u over here. We're going to choose u to be arcsine of x. If it bothers you to use the same variable, you can switch the variable and you can call it something else. You could call it omega if you want to, or w. It doesn't have to be a u. Now we have arcsine. We can take the derivative of both sides of this new u, and this gives us the derivative with respect to x of arcsine of x. We know then that du dx is equal to 1 over the square root of 1 minus x squared times the derivative with respect to x of x, which is 1. So du over dx is equal to 1 over the radical 1 minus x squared. Now we can abuse the notation and we can move the dx to the right. Now last time we just kept that and we substituted that for du. You can, however, if you want, go ahead and solve for dx like you've done in the previous examples. If you do that, then you get that dx is equal to the radical 1 minus x squared times the differential du. Now we have something to substitute for this arcsine of x, and we know that we can represent dx with this radical times du. We also have limits of integration, though, from 0 to 1/2. We're going to need to change these. Now we're going to come here and we're going to figure out what those limits of integration change to. But first, let's rewrite what we have so far. We have not changed the limits of integration, so they are still x values from 0 to 1/2. We have the tangent of u divided by the radical 1 minus x squared, then replacing dx with the radical 1 minus x squared times du. The radicals cancel, and we end up with the integral from x equals 0 to x equal 1/2 of tangent of u du. Everything is in terms of u except the limits of integration. We need to go back to see what our u was so that we can substitute. Our relating equation is the u is the arcsine of x. Let's write that down below so we can remember it. U is equal to arcsine of x. When x is equal to 0, u is equal to the arcsine of 0. That's the angle between negative pi over 2 and pi over 2, whose sine gives you 0. Well, the angle whose sine is 0 is 0. So this tells me that u is equal to 0. So replacing x equals 0 will be u equals 0. When x is equal to 1/2, then I have u is equal to the arcsine of 1/2. This is the angle between negative pi over 2 and positive pi over 2, whose sine gives me a positive 1/2. Because it's positive, it has to be in quadrant 1. And because it's 1/2, the angle has to be pi over 6. So this tells me that u equals pi over 6. Notice that this limit of integration is not the original limit of integration. It's not the 1/2 that we had at the beginning. And that's because we changed the value to being a u value. Now we can write the rest of it, tangent of u du. Now, how do we integrate when we're looking at tangent of u? When we're looking at tangent of u, remember that we need to take tangent and we need to rewrite it in terms of sine and cosine. This gives me the integral u equals 0 to u equal pi over 6 of the sine of u divided by the cosine of u with the differential of du. Now we're going to do, yes, you've got it. This is a hard one. Another u substitution. What we want to do now is we'll use omega instead, since we've got too many u's running around. We're going to let omega be the denominator. Omega looks like a w. This becomes omega equal to the cosine of u. Then to complete the u substitution, we find the derivative of omega with respect to the previous variable in the differential, which was du. This gives me the derivative with respect to u of the cosine of u. D omega du then leads to negative sine of u. Since the derivative of cosine is negative sine, then we abuse the notation and move the du to the opposite side. This gives me that d omega is equal to negative sine of u du. Then I can solve for the differential du as I've been doing all night. And this gives me d omega divided by negative sine of u. The negative is a floater. It can be written out front or in the numerator or the denominator. Now I want to take the previous expression that I had here in the integral, and I want to rewrite each piece. I have the integral, I just switched my differential again from being du to now it's going to be d omega, but my limits of integration are u values. So now I need to switch my limits of integration again. So when I do that, I can come over here and say, when u is equal to 0, omega is equal to the cosine of 0, using the relating equation that you see up here in the box. The cosine of 0 is 1. That changes this limit of integration to omega equal 1. When u is equal to pi over 6, then omega, which is the cosine of u, becomes the cosine of pi over 6. The cosine of pi over 6, remember, is square root of 3 divided by 2. It is the long side of that long, short triangle. This gives me omega equal the square root of 3 over 2. Now I want to look at substituting the rest of it. I have sine of u over cosine of u, but cosine of u becomes omega. Then I want to replace the du that I have here with the expression that I have here for du, which is d omega over negative sine of u. Notice that the sine of u's cancel out, but I still have the negative. I can either leave the negative or I can switch the limits of integration to take care of the negative. Let's first write it with the negative still in there, and then we'll swap the limits of integration so that we can take care of the negative. This is negative d omega over omega. This becomes, if I switch the limits of integration from omega equal root 3 over 2 to omega equal 1 of d omega over omega. Now you should recognize that one. You know that the differential divided by the variable is going to involve natural log. So now we have the natural log of the absolute value of omega evaluated between square root of 3 over 2 and 1. This gives me the natural log of the absolute value of 1 minus the natural log of the absolute value of radical 3 divided by 2. Now you should remember that natural log of 1 goes to 0. This gives me negative natural log of radical 3 over 2. The absolute values can be dropped, and I can write this also in terms of a difference. Remember that when you have division in the argument to a natural log, it becomes subtraction of the factors. The negative on the front is going to stay on the front. And then I have the natural log of the square root of 3 minus the natural log of 2. If I distribute the negative, I can then write that this is the natural log of 2 minus the natural log of the square root of 3. You could also write the square root of 3 as 3 to the 1/2 power and pull the 1/2 to the front. That, however, is not necessary, though it is certainly possible. I think we've done enough examples on this. It is important to know, but it's not the most important. The most important technique we've learned here is integration and u substitution. I hope this helps you to match the patterns to use a formula from an integration table. In the next video, we'll be taking a look at the area between two curves rather than the area between a curve and the x-axis.